Okay, my name is Bertrand Marquis. I'm a principal software architect at ARM. I'm focusing mainly on domain safety and virtualization technologies on ARM. And one of the projects I am working on is the FFA specification. I'm also a maintainer of the Xen project on ARM. So today I will present you the firmware framework for ARM profile, why it was created and what it provides, the benefits it could bring for Xen and hypervisor in general, the status of the implementation in Xen, and at the end some open problems we have with the specifications and hypervisor, so that I'm opening the discussion for a design session after. So, on ARM, we have something named Trust Zone, and the secure world is becoming bigger and more diverse. So right now, in a typical system, we have something looking like that. So we have, in the secure world, a trusted operating system like Opti. And in the normal world, we have one client, which is usually a VM with Xen, using the secure services provided by Opti. So this is how the world is looking now. But we see more and more outside that new targets, new architectures that are built based on Trust Zone are becoming more complex. The first part of it is that not only one VM needs to use secure services, but all VMs needs to use it for several things, like using encryption services, using key management, using secure payments, or using DRM technologies, which are provided by the secure world. As a consequence, on the secure world, we see that there are more and more providers. So software is coming from different sources, from the OEM, from the SIP, but even from the operating system, in the case, for example, of DRM. So this new complexity is bringing a lot of new challenges to the software architecture or the software stack in general. We now have multiple firmware components which are coming from different sources. So in the current way of building the software stack, there is no real isolation provided inside the secure world, which means that an application in a trusted OS can impact another application in the trusted OS. There is no isolation between them. And the trusted OS itself could in fact impact the EL3 firmware. So in the current stack, everything needs to be secure and trusted on the secure world as a big block. In the normal world, there is also some potential issues. And the first one being that the secure world can access every non-secure memory and feature. So that means the secure world can actually impact the non-secure world, which has some consequences, for example, on safety. The other one is that if there is an issue in the secure world could be used to impact another VM. So there is a communication channels in which one VM could use the secure world to actually impact another VM, breaking the isolation provided by the hypervisor. So all those issues are increasing the software complexity and the attack surface a lot, which means that the software in the secure world is being more complex and harder to audit for security, but also for safety in the future. One other problem that we have with the current way the Trust Zone technology is used is the fact that the communication with the secure world is not standardized. And as the software stack is becoming more complex, the places where there are T-specific drivers on the software stack is becoming big. So you have one T-specific driver in the operating system on the normal world, you have one in the hypervisor, in Xen, for example, you have one in the firmware, and then one in the trusted OS. This is kind of a shame because all of those communication protocols are trying to answer to the same problematics. We want to communicate between the secure world and the normal world. And all of those are based on exactly the same principle. Usually, you have some kind of SMC-based communication to get exceptions to go to the EL3 level, and you need to access some normal world memory from the secure world. So they all use the same model, which means that it's a shame that there is no standard. And in the industry, if you want to switch from Opti to Trusty from Google, for example, you have to change the drivers in all components involved. So change the driver in the hypervisor, in the operating system inside the normal world, but also in the firmware and in your trusted OS, so that you can build up your communication. So this is where we started to think of the FFA standard to simplify those things. So the FFA standard, so first FFA is standing for Firmware Framework for ARM A profile. There are too much F. And it has three main goals. So the first one is to isolate the software components in the normal world, so VMs, providing the services to several VMs, but also in the secure world, so that we can have elements in the secure world coming from different providers and have a standard way to isolate them in boxes. The second goal is to standardize communications. So first between the normal world and secure world, but also between components inside the secure world or even inside the normal world, so that the FFA protocol can be used to communicate between VMs, between a VM and the hypervisor, or between the hypervisor and the firmware. And the third goal is to align to some of the applicable PSA security goals. So PSA stands for Platform Security Architecture. That's a standard to which you can certify your platforms through ARM to have some security features. So there are three goals that we aim to achieve with FFA. That's device support isolation, support for transaction over isolation boundaries, and support some cryptographic features. So what is FFA? So first, FFA is introducing some terms to identify the different components on the system. First one is SP, which stands for secure partition. So this is where on the picture that's on the right, this is where you will put your trusted execution environment. So for example, like Opti. So each SP, which are partitions, are following the FFA programming model. And you can implement inside those SPs different services which will use FFA as a transport mechanism. So each trusted OS should have an FFA generic driver. Then we have the SPMC, which stands there. So the SPMC stands for Secure Partition Manager Core. That's somehow the equivalent of an hypervisor in the secure world. It is generic, independent of the TE's implementation, and its goal is to transfer FFA message with some checks and some conversion inside the message. It's an optional component for two reasons. First, you might not have secure EL2 implementation in your CPU, which is something not present in most CPUs right now, but which will come more in the future. And the second one is based on your platform. You might not need to have several trusted OS in the secure world, which means the SPMC might not be needed. But the standard is aiming at this. Then we have the SPMD, which is basically the firmware component. It is just relaying messages from secure to non-secure or non-secure to secure. And it contains a standard component to have FFA support. It's right now supported in standard in trusted firmware A. Then we have the hypervisor, which would have a generic FFA driver, and then the final guest OS, which would have an FFA driver, which will be used as transport to provide several services. So the advantage of all this is, as you see on the picture, to have FFA standing on any communication layer between components, so that all of this becomes standard and everything is interchangeable. So if you change a hypervisor, as long as it is compliant with FFA standard and following the FFA protocol, then it will be completely transparent for the operating system. In the same way, if you have no hypervisor, the FFA standard is made so that it's completely transparent for the operating system running on top of the firmware. So we aim at standardizing the interface. So FFA provides first secure partition in the secure world with SPMC acting as the equivalent of an hypervisor to provide sandboxes with isolated array space and maintain boundaries between those boxes. Then we have a partition runtime model where we describe the state machines of the secure partition. We have a concurrency model so that you can have single core or multi-core secure partition in the secure world. And we keep the existing runtime model existing with TrustZone, which means the normal world is still the one responsible to provide CPU cycles to the secure world. There is no notion of parallelism there. We also have an interrupt management model, which means it's possible for the secure world to get an handle interrupt that's handled in the scheduling system. And then we provide communication system, so synchronous or asynchronous messages based on registers or shared memory, and a doorbell system for signaling. We have some memory management, which allows you to share, lend, or donate memory from a component to another component, which means from a VM to a secure world, or from a secure partition to a secure partition. And finally, we have an endpoint identification system based on UUID. Means that you can discover services and use services without a knowledge of where the services lands on your whole platform. So what are the benefits for Xen and hypervisor of the FFA standard? So currently in Xen, what do we have? We have one Opti driver. It's specific for Opti. It's not working with any other Opti on other trusted execution environment. It's not widely used. So if you want to use Trusty from Google, it does not work with Xen at the moment. Second problem we have with the current implementation is that the VM support is experimental. Basically, you can use Opti services from DOM0, but it's impossible to use Opti services from a VM. Even in Opti, the support for VM is experimental at this stage. So there is a quite maintenance cost. It's Opti specific. We depend on the Opti project. They can change the protocol any day. They will not. It's quite stable, but still. FFA will bring a generic FFA driver in Xen. So that would work with Opti, but that would also work with any other FFA-compatible trusted environment. FFA has native VM support, so it will be possible to use services, secure services from DOM0, but also from any guest that has FFA support. FFA would ease the maintenance for Xen. We would not depend on an external project, but we would depend on an external specification, which is more stable, which means we can test up to the specification. We don't need to test more than the specification. The FFA protocol also has quite an advanced version control system where actually you don't need to support all versions of FFA. So FFA version are backward compatible, and you have a negotiation system so that a guest could support FFA 1.0 and another one 1.2. It would still be possible to handle quite easily in Xen. Finally, in the long term, FFA is potentially usable between VMs. So we could use the FFA protocol to actually have communications between VMs and not only between a VM and a secure world. What is the status of the implementation? So we have an FFA series under review right now. V8 has been reviewed. V9 is on its way. There was something with the Arch domain teardown request that we are handling at the moment. Our goal is to have a tech preview in the next release of Xen. FFA series that we pushed currently has all the minimal support required so that you can use it with Opti. So it will be possible to keep the current support going to FFA in the future. It's supporting the version 1.1 of the FFA specification. 1.2 version is for the end of the year. It has some limitations. Some of them we will discuss after, but regarding the size of the transfer buffers, some cleanup problem when a guest is stopping abruptly, and some long critical sections, and the text preview at the moment. FFA is also supported in all the external projects that we need with Xen. So it's supported in trusted firmware and was released several times, several release cycles ago. Opti support for FFA has been reviewed and merged. It's not in the current Opti release, I think, but it will be in the next one. And in Linux, it is supported. There is one fix needed in Linux because there was a bug in Linux, but it will be in the next Linux version. Okay. So the FFA specification is being written, which means that we still have some challenges and some things that are not settled in stone and that we want to work on. And we think that the community could help us on that because some of them are hypervisor specific and the community has a knowledge on that. So if you are interested in some of the subjects that I will mention now, please come to the design session that I register after. So, some of those challenges are quite technical, so don't hesitate to stop me if something is not clear or if you want to have more detail. First problem we have is the mapping scatter gather list size. So what happens? When a VM wants to share some memory with the secure world, the VM is making a scatter-gather list inside a shared memory with Xen. This scatter-gather list contains list of areas of memory which are expressed in intermediate physical address, so guest physical address point of view. Xen takes this list and has to convert this intermediate physical address into physical addresses, and is creating a list in its own exchange buffer with the SPMC on the other side. Problem is that one list in the guest buffer can turn up in a very big list between Xen and the SPMC, which means one message coming from a guest might have to be split into several messages so that we transfer this mapping request to the secure world. The problem of that is that is creating a long critical section inside Xen. We will have several exchanges between the secure world and Xen until those mappings are actually created on the other side. So there are open questions, and we are welcoming ideas on how to fix that. So there are several possible solutions. One is to limit the buffer size between the VM and Xen, and between Xen and the SPMC, to kind of make sure that everything could fit, but the size could be quite big. The other one is to force the guest to just give us a scatter-gather list which is organized in pages. This way we know that we will have one intermediate physical address corresponding to one physical address. But this could lead to very, very long list if a guest wants to share gigabytes of memory with a secure world, where with an entry in the scatter-gather list currently, you can do that in one call. And I'm open to other ideas if anybody has some. Okay, this is something we will discuss later. Second problem that we found is mapping cleaning. So use case is you have a guest in Xen. Guest shared some memory with the secure world. The guest is killed or is dying or is panicking or is normally stopping. When it stops, this memory is still mapped in the secure world in a secure partition. For this memory to be available and reusable by Xen if we want to restart the guest, for example, we need the secure world to unmap this memory and to release it. So, idea, first one is to inform the ESP on the secure world that the VM died. So FFA is already supporting this. We are informing the secure world that the VM died. Problem is, we still don't know when this memory will actually be released. We have an example use case where a secure partition is actually using this memory for DMA transfer, and they cannot stop completely the device abruptly, so we need to wait for the DMA operations to be done. But we don't know when this will happen, and this is happening asynchronously. So we need to be informed. Problem is, if you want to restart the guest, you cannot do it. The memory is not available yet. So solution would be to lock the memory until it gets released by the secure world, but who knows when it will happen. And if you have any other ideas, we are more than open. Another one is the interrupt handling. This one is kind of fun. So, what is the situation? You have an interrupt happening in the secure world. So the secure world is activated, is handling the interrupt. Returning, that's not the same scenario. An interrupt in the normal world is happening. So you were in a call to the secure world, an interrupt is happening in the normal world, so you go back to the normal world to handle this interrupt. Why do we do that? The goal is to respect real-time constraints and make sure that interrupts are not blocked for too long. So our call in the secure world is blocked because it was interrupted. The interrupt is handling Xen. Xen is saying, okay, this interrupt is actually for another VM, so I will activate the second VM. Second VM wants to use the secure partition which was blocked before. It cannot, right? The secure partition is still blocked on dealing the other call of the VM1. So the only solution to have VM2 actually doing its job would be to reactivate VM1. That's a priority inversion case. You have VM2 which has more priority, which needs VM1 to finish to actually do its job. Okay. So how can we solve that? So first idea would be to say, yeah, we will run the interrupt to completion. Yeah, but still, you will allow VM1 to handle some kind of long action in the secure world, which could potentially block VM2 to handle its interrupt in the time it wants. We could enforce in Xen scheduler to know that, okay, VM2 is asking a secure services on this specific SP. I know that this SP is blocked on a call coming from this VM1, so I will virtually reactivate VM1 to finish its call so that VM2 can handle this call. Might be good, but it's still a delay for VM2. Do we have other solutions? The question is open. Final one, and maybe the most fun one, is how to handle a T that we will put in a VM. So for those of you using trust zone technology, it's actually quite simple. That's an exception only. So basically, you use register, you go directly to the secure world. Secure world gets the register status under the call and goes back to the requester. Now, if we want to do the same process between VMs, we would have to do some kind of exception handling inside the VM so that we can pass the registers. We can simulate this through interrupts, maybe. We can say that, okay, we will not handle synchronous calls between VMs through FFA, only a synchronous call, but that means you have different functionalities depending on where your Ts are actually put in your system. We need to find a solution for that so that FFA is completely possible to use between VMs or SP in a completely transparent way. Okay, so I'm just presenting the problems here. The goal is to be able to discuss them in a design session later. Thanks everyone, and do you have any questions? Yep.
So is there another team besides Apple that's already FFA?
Yes, there are several of them. Google is working on making Trusty FFA compatible. And several ARM partners are working on making their own internal trusted execution environment compatible with FFA. The FFA specification is developed in a partnership with several partners of ARM, Google being one of them, and it's quite open. For example, Google is trying to put FFA support in PKVM inside the Linux kernel at the moment. And several others have their own proprietary trusted execution environment, and they want to use FFA in the future for exactly the reason that I presented to reach the three goals. Yeah.
So what share memory to the one that can throw it away, the memory is zero? Do we keep reference of those pages before sending them out to the...
Yes. That's the problem. The problem is right now, even though it's marked this way in Xen, the question is how do we somehow retrieve those stuff? So the only solution that we have so far is to create an RCU task and go ping the other side from time to time to check, okay, did you release it? Did you release it? Oh yes, you did release it. Okay, yes, I can restart my VM. Yes. Okay, it's been 2 years, that's a bit too long. So that's why it's an open subject. There are plenty of solutions. We are investigating solutions like, okay, maybe we need a way for secure to signal non-secure in the other way around. But right now, this exists, so we have doorbell systems, but those doorbell systems are only made to signal from an SP to a VM. There is nothing sort of at this stage to signal from the SPMC to the hypervisor. We are starting to introduce virtual SPs, which exist in the SPMC, so that those could signal something, but we don't have the equivalent inside them. Might be something to check. Sure. Yeah.
How common is FFA call inside actually, I think a blocking
Okay. So, there are two cases I mixed up. I don't want to present the other cases where an interrupt is received by the secure world directly. Here it's an interrupt targeting the normal world. So you, example is you have a partition wants to encrypt a big amount of data in memory, and you have software encryption mechanism inside an SP. So you call the service inside an SP, but in another partition you have a real-time sensor which is saying something changed. So you receive an interrupt. In the FFA protocol, we managed to include this so that the secure world execution gets blocked, so that you go back to the normal world and handle this interrupt as soon as you can. So it's pretty common.
That makes sense to me. The problem makes less sense because, as you said, why someone without real-time requirement will make SSA call on the real-time?
The problem is, it might be another VM which has a real-time requirement. And you have a second VM on the side that you are running in parallel, which might not have. We might circumvent this by saying, okay, we will put a recommendation that if you have some real-time requirement, you should not allow any FFA services to be used by another VM on the same core. That's definitely one of the solutions, but there might be others. And for example, well, I want to leave the discussion open, but this is, okay, that's kind of the easy solution. There are other solutions like enforcing on ASP. If you have this kind of stuff, you could also say, okay, you have to duplicate your ASP so that even if the ASP was blocked by another VM, you can use another ASP to actually provide your services. So design-wise, from an integrator point of view, there are lots of solutions. The question is, should the spec define a little bit more so that this problem is actually handled from the spec at the very beginning and the integrator does not have to ask himself these kind of questions? Yep. Oh, we forgot to take the microphone.
Okay. Could an Android ARM system with Google PKVM avoid using secure world entirely? For example, to disaggregate security functions into PKVM privileged VMs? Sorry.
At the moment, they cannot, and they don't want to. It's a valid design question, but moving secure services inside a PVM or a VM for that matter would mean that you don't benefit anymore from the security and the isolation brought by trust zone. That's not a goal at the moment to use FFA technology to completely remove trust zone. That's kind of the opposite. That's to ease the use of trust zone from the normal world. To some extent, there are some use cases where it could be beneficial to be able to use FFA services between VMs. But in this kind of applications, Google is definitely not looking at those solutions. They are looking more at the possibility to use secure services from a PVM, which is their problematic at the moment. There are some things, for example, DRM technologies, payments, and things like that, where they don't want to, nobody wants to take the risk to put that out of the trust zone area, because trust zone is not only bringing features from the security from the CPU point of view, but usually also from the peripheral point of view. You flag your payment system as secure and it cannot be accessed from the normal world. So you reduce your attack surface by doing that. Is this answering the question? No, it does not? Okay. No? Okay, then I will consider that as it's an okay answer. Anybody has any other questions? No? Then, thank you everyone.